Okay, I think we've hit 11:01 and people are still coming in, but let's get this kicked off. Again, my name is Tom Arnold. I'm co-founder and CEO of Gridium. This is part of our continuing webinars on reacting to COVID and adjusting to the new normal that we live in. One topic that has come up over and over again is UVC and other types of treatments for the air conditioning system. And I'm very excited to have this discussion today with Chris. This will, by the way, just a few administrative items. As usual, this will be recorded. We'll post it so you can share it with colleagues. We typically transcribe these as well for those of us that prefer to read. And of course, I do anticipate quite a few questions today. So if you've got questions, get them ready in the question panel, and we'll cover them. And Chris, I might interrupt you if the question is particularly germane to where you are.
Yeah, please do. Please do.
I think everyone knows me, but just to introduce Chris, if you want a new material in California, you go directly to Santa Barbara. That's where all the great science happens. Chris is a PhD candidate in the materials department at UC Santa Barbara in the fields of solid state lighting and energy and electronics, which is obviously relevant in this field. His research it does also come from other places as well, both Cornell and New Mexico, where I'm sure you enjoyed some green chilies with with Millen. For those of you that know, Millen is very fond of New Mexico as home state. So Chris, welcome, and let's get started and dig in. Let's hear the latest research and what exactly is this UV disinfection that everybody's talking about, and what's going on in the field of research.
All right, sounds good. So let's just jump right in here. Hopefully everyone's able to see my screen now.
Yep.
So thanks, Tom. Thanks, Millen, for having me on. I'm really excited to be here to talk to everyone about a little bit about my work in ultraviolet science, and also just more generally things like UV disinfection and how they can be used for air conditioning applications specifically. So this is UC Santa Barbara. We're right on the beach. This here is SSLEEC, or SLEEC as we call it. So about 100 yards away from the beach. This is where I do most of my research. So let's just jump right in. I wanted to start with a quote from an article that I read recently that I think might be relevant to some audience members today. So I'll just start by reading that. So this person says, "Oh geez, I think there's a new option every single day. I've got somebody calling me from a block's number telling me they want to sell us services, and some of these things don't even exist yet. So vendors are claiming that they can have something that doesn't even exist, or maybe they're making claims that haven't been scientifically proven. And so this is really a wild west right now when it comes to ultraviolet disinfection, and I'll explain what I mean by that. But right off the bat, I want to start with just the basics. So does UVC work? Does it kill germs? Yes. The answer is absolutely yes. UVC is a real technology. It's been around for over a century. So there's no question that the science of UVC disinfection is real and it works. Now, the question, will a UVC system work for me? Well, that depends. It depends on what you need from this system. It depends on what system you're referring to. And that's obviously a much more complicated question. So myself as a scientist, most of my work is focused on that first point, right? What is the science of UVC? And I really am not really the foremost expert in larger systems, right, such as air conditioning systems. That's something that probably many of you in the audience might know more about than I do. And so my goal today is not to tell you about any one system that works or any system that doesn't work. My goal is to share with you some of the technical details about ultraviolet disinfection, so that you can then make an informed decision about whether a particular system makes sense for your application or not. So I just want to give a quick shout out to SSLEEC. This is a research center at UC Santa Barbara. So it's a partnership between academic scientists and industry partners. So we work very closely both with academic professors and industry researchers. I've shared a couple links here. So I've linked just our general website, and I've also linked a crowdfunding website where you can support our research if that's something you're interested in. And at SSLEEC, what we're focused on is a material. So as you know, this is the materials department. The material is called gallium nitride, and it has a lot of really interesting uses in the energy efficiency space. But the most interesting use is light emitting diodes. And my research, and so this is how I came to the ultraviolet area, was via light emitting diodes, and specifically ultraviolet light emitting diodes. So I'll speak briefly about those later. But first I want to start with just the basics. What is UVC and why is it different from UVA and UVB? You've probably seen these terms being thrown around, and it's not always specified what those things actually mean. So ultraviolet light is, of course, a type of light, and like all light, it's made of waves. And what that means is that it has a specific wavelength. So a certain very small portion of light is visible to the eye. We call it visible light, and it corresponds to wavelengths between 400 and 700 nanometers. If we look at the part of the spectrum with slightly shorter wavelengths, beyond the violet, we get to the ultraviolet. And so I've zoomed in on that part of the spectrum here, and you'll see that the ultraviolet spectrum closest to the visible spectrum is called UVA, and then the further you move away from the visible spectrum, the more you increase in energy per photon. So the more energetic the photons are getting, you get towards UVB and then eventually UVC. So these are just names, right? That what really matters is the wavelength or the photon energy, and we've just come up with these names: UVA, UVB, UVC, and you can think of these as being like colors within the UV spectrum. And one question that I get a lot is, well, so I've heard that UVC works great for disinfection, but what about UVA or UVB? It's all UV, right? It's all kind of the same. And the answer is no, that's definitely not the case. And to illustrate this, I'm showing you the difference that 150 nanometers can make. It might seem like a small number, but it's the difference between going all the way from blue to orange. So it's quite different. If you went online and ordered a blue shirt and then in the mail you received an orange shirt, you would say, hold on a second, this is completely wrong. This is not what I wanted. So that's how different UVA and UVC are from each other. So we really are talking about UVC here. To further illustrate the difference between the three regimes of ultraviolet radiation, I'm now going to show you a graph of germicidal efficiency for each of the three different regimes. If we start on the right with UVA, we get a lot of UVA from sunlight. It has basically zero germicidal effect. As a scientist, you're not really supposed to say anything ever has zero effect, because there might be some very tiny effect. But practically speaking, UVA is not really going to do anything to kill germs in a real world application. UVB can have some germicidal effect, especially if you are in a carefully controlled laboratory setting where you can combine it with some chemistry. In certain cases, UVB can give you some germicidal effect, but really the gold standard in UV germicidal efficiency is UVC. It has a very strong germicidal effect. It's universal across all types of germs because it attacks DNA directly. So anything that has DNA or RNA will be effectively killed by UVC. And you don't need any chemistry or any other laboratory-specific conditions to get it to work. The next question that people ask very often is this reliable? I mean, is this something that we know works well, or is this some sort of brand new technology that hasn't been proven yet? So UV disinfection actually goes back to the 19th century, and so in the late 1800s it was first discovered, and then 1903 Niels Finsen received the Nobel Prize for it. And right away, I mean immediately, right in 1903, it was recognized that this could be used to treat diseases. And there was a lot of excitement about it, and it actually was very quickly implemented in hospitals. So as early as the 1930s, you actually had ultraviolet lamps being used for air disinfection in hospitals. Then in the 50s and 60s, with the advent of antibiotics, ultraviolet disinfection sort of fell out of favor because people sort of thought you could just use antibiotics for everything and you wouldn't really need it anymore. Then in the 80s, a few things happened. So on the one hand, I'm showing the picture here. It was realized that UV could also be used to effectively disinfect water, and immediately became very widespread on regional and municipal scales for water disinfection. And what also happened in the 80s was a resurgence of TB and a few other antibiotic resistant viruses or germs, or so-called superbugs. And so starting in the 80s, you had the beginnings of a return of ultraviolet disinfection, because unlike antibiotics, there's no such thing as a UV resistant germ, or at least none that we've discovered so far, because again, it attacks germs on the level of DNA directly. So anything that has DNA is going to be sensitive to UVC disinfection. By the 2000s, this became pretty widespread in certain niche, small-scale medical applications. And then about 10, 15 years later, it first started to trickle into the consumer market. And what really enabled that transition was the invention of ultraviolet LEDs. LEDs are much smaller than lamps. They're able to be more portable. They can be turned on and off on demand. And so all of these factors combined to give you the beginnings of a residential or at least consumer market, point of use market for ultraviolet disinfection. And finally, fast forward to today, 2020, and we now have the COVID epidemic and all sorts of UV products that are directly targeting COVID applications. So that's sort of a
Hey, Chris,
timeline.
before you move on,
Sure.
One question here is, we've been all taught in this crisis that sunlight is a very good disinfectant, and the risk of outdoor transmission is low, et cetera, at least partially because of sunlight. That's UVB, not UVC, right? There's a question from an audience member on that.
Yeah, that's a great question. So sunlight is not a disinfectant in the same way that UVC is. So sunlight is about 95% UVA, 5% UVB as far as the UV portion of sunlight. What sunlight does mostly is it evaporates moisture. And as we know, moisture is droplets, right, are one of the key ways that viruses are able to stay alive in air and on surfaces for long periods of time. So just the what's called the desiccating or the drying out effect of sunlight will give you some weak germicidal effect. The main reason that being outdoors limits the spread of the virus is actually mostly just because you have all this fresh air. Yeah. And so any virus particles that you might expel are very rapidly dissipated and are unlikely to spread person to person in any large concentration. But when it comes to germicidal action, sunlight, again, doesn't really do much directly, certainly not on the time scales of UVC. That's one thing I haven't mentioned. So UVC will kill viruses on a time scale of anywhere from 30 seconds to 5 minutes. So it's pretty fast, whereas sunlight would take hours or days.
Yeah.
So it's sort of in a different category for that reason. Yeah.
Great. Thanks.
Yeah, great question. Thank you. So I wanted to briefly talk about the mercury vapor lamp. And the reason I work on LEDs, I like LEDs, but the reason I'm focusing on this is because right now the LED technology is still pretty new. And so if you go out into the marketplace and look for a high power UVC disinfection system, what you're going to get is a mercury vapor lamp most of the time. So the way these vapor lamps work is that you have an AC voltage coming from a tungsten metal wire inside of the lamp, and similar. So inside of this mercury lamp is mercury gas mixed with some other gases, and what happens is that when you pass an electrical current through it, the electrons collide with the mercury gas atoms, leading to a chain reaction and releasing energy in the form of light. And I've also added here that there are multiple layers of quartz and glass to prevent leakage of mercury, which is toxic, obviously. and to filter out unwanted wavelengths. Filtering out unwanted wavelengths is important because if you allow the wrong wavelengths to escape from this lamp, there's some risk that it'll generate ozone. That's another question that I get quite a bit is, doesn't UV generate ozone? And the answer is the wavelengths that generate ozone are quite short, are below 200 nanometers. And so there's no overlap between the ozone generating light and the germicidal light. So any modern mercury lamp based system, or even LED system, any modern UV disinfection system, 9 times out of 10 will have zero ozone production. You'll want to confirm that with the manufacturer, of course, but you can safely assume that any modern system with the correct safety features will not be producing any harmful levels of ozone at all.
That's really good information. That's come up in prior webinars because, of course, ozone is a lung irritant, which is not what we're looking for these days.
Yes, that's right. You definitely would not want to use a system that produces ozone. So that's an important thing to think about. Okay, so just a few highlights about vapor lamps. So in many cases, they're quite delicate. You don't want to be touching the glass surface. So what that translates into is you need trained professionals to install and maintain these systems. Typically, what I've seen quoted is about a 1-year replacement lifetime, which may not seem too bad, but if you imagine an entire building with maybe dozens of these lamps, that maintenance could become quite significant. The efficiency is only 30%. So just by comparison, if you were to buy an LED light bulb for lighting in your building, that would be closer to 70% or even higher than that efficiency. So we hope that UV LEDs will be able to do much better than this in terms of energy efficiency. These lamps also have a long warm-up time, so you can't simply switch them on and off on demand. So if you imagine an air conditioning return system that the return air cycles on and off, you can't just turn the lamp on and off to cycle with the return. You actually have to keep the lamp on at all times or allow a long warm-up time. So that's a bit of a disadvantage. And of course, it contains mercury. Mercury is toxic. Most systems are safe and the mercury is well contained, but you also might want to keep in mind that there are some international treaties saying that mercury needs to be phased out. I haven't seen much regulatory movement on this yet, but I wouldn't be surprised if there were some increased regulations on mercury in the coming years, especially as alternative technologies such as UV LEDs become more and more feasible. So that brings me to UV LEDs. As you may know, my research advisor, Shuji Nakamura, and his colleagues invented the blue LED in the early 90s, and that really has led to a revolution in lighting as we've gone from light bulbs to fluorescents to LEDs. And we've gotten to a point now where LEDs are so advanced that there's really no application where they don't, or I should say there are almost no applications where LEDs don't outperform all other visible light sources in pretty much every way. So brightness, efficiency, lifetime, pretty much everything you could think of, LEDs are going to outperform any other lamp-based light source. And the expectation is that UV LEDs will follow a similar trajectory. There are some technological challenges that need to be addressed for that to happen, but we at SSLEEC fully expect that UV LEDs will very rapidly begin to replace mercury vapor lamps as the primary source of UVC light. So just a few highlights. It is a new technology, so the cost is still high and the efficiency is still low, but very soon we expect to achieve all the things that visible LEDs achieved, such as longer lifetime, better energy efficiency, lower cost. There's no warm up and there's no flicker, so this enables smart functionality, dimming, all those sorts of things, and controllable wavelength. So you can specifically control the wavelength in a much more precise way than you could do with a lamp. So finally, I'll move on to what everyone's probably most interested in today. How does this work in the real world? And specifically, how can it help against COVID-19? And it's important to keep in mind that some of these systems make more sense specifically in fighting against COVID, whereas other systems might make sense just generally. They might just be good systems to implement, even if they don't necessarily specifically target COVID-19. So that division between COVID specific and just general good practices to follow for health and hygiene is a distinction I'm going to try and make, and hopefully I'll be clear about when I'm talking about just general pros and cons of different systems and when I'm talking about COVID specific. But please ask me in the questions if I'm not being clear. So I want to share a story about out of Germany. Germany is often listed as an example of a country that's done quite a good job in containing the COVID outbreak. And there are many factors that go into that. But one of them, of course, is government regulations. But they did have an outbreak, and this is a few months old now. I made this slide a few weeks ago, but I still think it's a relevant story. So at a meatpacking plant called Tenias, thousands of workers, there was an outbreak of thousands of workers getting the virus, and the German government, this led to a huge outbreak in the entire region, right? So 500,000 people were under lockdown at the time. And the German government actually was thinking about holding this company liable for public costs incurred due to the outbreak. So this really became a huge deal. And the question that comes to mind is, what could Tenias have done? Is there something that they could have done to prevent this outbreak? And the biggest question for us today in this conversation is, could UVC have played a role in preventing this outbreak? So before jumping into whether or not it would have helped, I think it's important to keep in mind that when we talk about UVC disinfection, we're actually talking about three different technologies: surface disinfection, water disinfection, and air disinfection. So when we talk about water, again, like I mentioned, this has been in widespread, large-scale municipal use since the 80s. It's a very reliable technology. It's well regulated, and now with the introduction of LEDs, it's beginning to find more and more residential use as well. So this one, I'm sort of giving a green light to indicate that this is reliable, this is ready to go, and there are a lot of good products out there to use. Surface disinfection is the oldest technology out of the three. This is the one that was first awarded the Nobel Prize for in 1903. It's easily tested in the lab, and there is a lot of proof that it works well in the lab. But it's also not quite as useful as water disinfection pre-COVID, and so it found limited use, and there wasn't much of a commercial market for it before COVID. And so as a result, it's not quite as well regulated, and I'm giving it sort of a yellow light here to say that the technology is real, the technology can be trusted, but it's hard to say whether any particular product is going to work or not, just because there's so many new products popping up now ever since the COVID outbreak occurred. And sort of as an analogy, I'm giving the chemical equivalent here, which would be wiping a surface with bleach, right? Whereas for water, the chemical equivalent would be mixing in something like chlorine. So finally, moving on to air disinfection, what we're all interested in. As I mentioned, this was also used widely in hospitals starting as early as the 1930s and faded with the invention of antibiotics. The problem with air disinfection now is that there really aren't many regulations on this from what I've seen. And it's also much harder to test in a lab than something like surfaces or water. And so for that reason, I'm giving it this sort of red light indication which doesn't mean there are no good products out there. There certainly are products out there that will disinfect air, no doubt about it. But because the regulations are not so clear, and because there might be a lot of fraudulent products out there, I can't really give this one a green light, COVID specific. On the other hand, non-COVID specific, just as a general product for health and hygiene, if I were giving this slide pre-COVID, I'd probably give this a green light, because there are a lot of really, really good benefits to air disinfection outside of the context of COVID. So I just want to be clear here that the caution that I'm giving here on air disinfection is really COVID specific. So why is air disinfection so much harder to prove and measure than the others? Well, the reason is because when we say air disinfection, we're not really talking about air disinfection. What we really mean are large droplets, small droplets, and aerosols. So droplets, obviously, we all know what droplets are. What an aerosol is is when most or all of the moisture in the droplet evaporates, if there's anything still left over that's light enough to float around, that tiny particle, which might contain some virus material, can stay airborne for a very long time. So that's what we're talking about when we say aerosols. But because, as this indicates, there's a large variety of different types of airborne transmission, it's hard to just take one of those and study it in a lab and then draw wide conclusions about air disinfection as a whole. So moving on to air conditioning, right? The reason we're all here today is to discuss air conditioning applications for UVC. And it turns out there are actually two major categories of air conditioning applications for UV disinfection. And one of them actually isn't air disinfection at all, it's surface disinfection. And so this is the box on the left here. And the idea is that instead of disinfecting the air directly, you use filtration to clean the air, and then you use UV to then clean the surfaces inside of the disinfection system. So there are a lot of benefits to this. For example, it can reduce the buildup of mold, which could improve health and reduce odor. And according to the company that makes these products, can also increase efficiency and reduce the amount of maintenance that you need to do on your system. So there are a lot of pluses to this, but it's not really going to do much to attack the COVID problem, because again, this is going to be focused on keeping the surfaces inside of your AC system clean. On the other hand, direct air disinfection, which requires very high power lamps, this is again what I referred to before as a little bit of a wild west. There's not really much scientific data about it. There's not much government regulation on it. And it's really hard to say how effective a system's going to be. I'll get into, in a slide or two, I'll get into why that is. But a good rule of thumb to keep in mind here is that when you're talking specifically about COVID-19, bringing in fresh outside air will almost always be safer than trying to disinfect air. So even the best disinfection system in the world will still leave some tiny fraction of virus in the air, right? So you might see something certified to kill 99% or 99.999, et cetera, right? So these systems are going to be great for reducing the amount of germs in the air. But if you really want to get to the cleanest possible air, and again, I'm talking specifically about COVID, bringing in fresh exterior air will almost always be a better deal if that's possible in your application.
So let me pause here because we're getting to some questions. If you can go back, because everyone likes air handler graphics here. So on your air handler slide. So
this one here, yeah, this is not my graphic. I have to admit, I took this from a manufacturer who makes this.
So the question here, and it was asked earlier in the session, maybe jumping ahead a little bit, but if a UV system is installed in the supply duct, how effective would it be given the short duration of exposure to the UVC wavelength? So let's talk about a couple of issues here. One, I think you're going to talk about dose in a second, but let's talk about supply versus return and these two strategies, and where would there actually be benefit? Theoretically.
So that's a great question. I'm not, just off the top of my head, I don't see much of a difference. We could use the analogy of water. So when you're disinfecting water, it's very important to filter it first and then expose it to UV. The reason for that is you need the water to be as clear and transparent as possible. So dirty water can't be disinfected by UV. Of course, with air, you don't really have that issue, although there might be some benefit to filtering it first. I would imagine that the biggest reason why almost all of these products are advertised as being for the return side is probably more because the more you can physically filter the air before it hits the UV lamp, the less sort of dirt and buildup you'll get on your UV system itself. So I would imagine this is probably just to reduce the amount of maintenance on the UV system rather than changing the efficacy of the UV disinfection itself. That would be my guess, but again, that's sort of outside my area of expertise.
Yeah, I mean, just to link a few comments from prior Gridium webinars, as some of you recall, when we had the ASHRAE fellow on, the consistent ASHRAE guidance is, as much fresh air as possible. And, there is no scenario where, the air 30 stories up in downtown San Francisco has COVID concentrations in it, because otherwise we'd all have it.
Exactly,
So,
exactly.
your advice here, I think, is consistent with ASHRAE, which is, look, if the fresh air is the biggest thing that you can do, on the return, then of course you get into filtration and potential applications. But again, that's the area that's so nascent in terms of where the industry has coalesced on these applications.
Right, right. So I think the idea of return air disinfection probably makes the most sense if you're in an application where you can't really bring in fresh air. So
Yeah.
obviously, if you're talking about an airplane, you can't just bring in fresh air from outside the airplane very easily. And so that's where things like HEPA filtration and other high efficiency filtration might make more of a difference.
Yeah.
But yeah, of course. I mean, that it's definitely the one consistent message I've seen time and time again is that bringing fresh air in from the outside is always the way to go.
Great. So Craig's other question here is, of course, hey, that run's pretty small. If I do my CFM calculations on that on the elbow, what's going on? So let's talk about
Right.
dose.
Right. Yeah, that's great. So that brings me into my next slide, which is dose, and that's my impression as well, is that that run is pretty small. So maybe most of you are already familiar with this idea of dose, but I just wanted to quickly use the analogy of a sunburn. So if you're out in the sun here in Santa Barbara, where it's very bright, even if you're only out for like an hour, that's still enough, at least for me, to get a sunburn sometimes. Maybe I burn pretty easily. On the other hand, if you go somewhere where there's less sun, but you're out 10, 12 hours, you can get a sunburn too. So it's really power and time that matter. And the same thing is true for UV disinfection. And so my impression, again, this is sort of more just an artist's rendering, right? I don't know exactly what this would look like in real life, but of course, you're going to want to maximize the dose by increasing the lamp power. And another thing that maybe isn't quite as obvious is reducing the distance between the lamp and whatever region you want the disinfection to be happening at. So, of course, it's not so simple. You can't just make the duct smaller, because then the air velocity will increase. And now you bump into your time constraint, which is the other thing, that you want to maximize the duration of exposure by, again, maybe this is an option in your application, maybe it's not, but if you could slow down the airflow or just maximize the distance over which the air is being disinfected, those are all things that are going to increase your dose. All of that being said, dose is very well understood for surface and water disinfection. We know exactly how much of a dose is needed to disinfect surfaces and water for pretty much every germ you could imagine, including coronavirus. However, I have seen very few studies on what sort of dose you need to disinfect air. And specifically, I personally have not yet seen any studies on how much of a dose you need to disinfect air specific to COVID. You can write down this equation, power times time equals dose, but actually knowing what dose you need is a completely separate question. So to answer this question, I think you really need to talk to the manufacturer and try and get as much information from the manufacturer as you can to see if they've actually done any testing, and kind of pick their brain on what exactly they know about dose, and see if they know how much is actually needed, because that's going to be hard to predict ahead of time, because for all the reasons I mentioned before, the science on air disinfection just hasn't quite caught up to where the science is on surfaces and water.
There's a question here that might be relevant, sort of, can you do anything in the ducting to help sort of reflect this light? A mirror tube or a light tube or something like that, so that the air would be more exposed. Again, interesting idea. Have you ever heard of that kind of idea?
Yeah. So that is a very good point. And I mean, again, I hate to keep going back to the example of water disinfection, but water is the gold standard for UV disinfection, and that's exactly what they do for water disinfection.
Yeah.
So there is a lot of science that goes into how to best design what's called a UV reactor, which just means what shape should the duct be, what sort of material should the duct be made out of. Maybe there's some sort of a path where the water will zigzag back and forth in some way. The angle that all of the walls of the reactor have for reflecting the light back and forth as much as possible. So this is a very important aspect of reactor design for UV disinfection, and it can be just as important, if not more important, than the power of the lamp itself. So that's water disinfection. I haven't seen when I was looking up products in the marketplace, I haven't seen much as far as reactor design on the air disinfection side. But certainly the answer is yes. You're going to want to make sure your duct is made out of some sort of reflective material. I'm not really sure what these ducts are typically made out of. Aluminum is actually the most reflective material in the ultraviolet C region of the spectrum, to my knowledge. So that's actually, if it's possible to use aluminum, that would probably help. Again, just off the top of my head, this isn't something I have specific experience with. You're going to want to maximize the reflections and minimize the absorption of light inside the duct. That's certainly true.
Yeah, interesting. What's fascinating is, of course, is this this disease is so new and it's so novel that we don't even have the bench science to do the dosing, which I think is just a tell for anybody that's approaching your building and saying like, look, I have the solution for you. If we don't have bench science, how could we possibly have a really robust solution in the marketplace?
Right. Yeah, and I mean, just to repeat again, the reason, so yes, the fact that the disease is so new is a big reason for this, but also, again, just to specify, in general, air disinfection is just a harder thing to study than surface and water. So
Yeah.
for surfaces and water, the science is pretty good on coronavirus. For air, it's just not quite as clear yet.
Yeah. Hey, the question coming in, by the way, that people are hanging on a comment you made earlier about, could take up to 2 minutes to disinfect. That's obviously, incompatible with moving any volume of air through. Do you want to explain that comment a little bit? I think that was in regard to surface disinfection, right?
Yeah, so that was specifically in regard to surface disinfection. And as this equation that's on the screen now suggests, that obviously depends on the amount of power you can deliver. So if it makes sense in your application to just have a row of multiple lamps and you can really crank up the power, then 5 times more lamps means 5 times, 1/5 of the time.
Yeah.
And so 30 seconds is about the fastest I've seen for surfaces. I guess what I would say is I wouldn't want to say that there's any magic number on how much time it takes, right? It's always the magic number is the dose.
Yeah.
And so it's obviously power dependent. But I mean, my intuition is the same. It seems unlikely that you're going to be able to get a significant amount of air disinfection in any real AC system where you have a high air velocity, where you're moving large volumes of air through a duct. It seems like it'd be hard to pull off, and I haven't seen any hard scientific results to prove that it works. Again, I'm not saying it doesn't work, so I don't want someone out there to say that I'm saying there's no way it's possible, because I'm sure there are good products out there that do what they say, but from what I've seen in the science, it's hard to be sure.
Yeah. Great. I mean, I think this gives our building operators the confidence to ask these questions. And if you're not getting a straight answer on it, then
Right. And we'll get to that in a little bit for sure, because as I mentioned towards the beginning, I'm glad these questions are coming in, because it's useful for me as a scientist to know what real world applications care about. But at the same time, at the end of the day, what you're really going to want to do is take these questions and ask them, like you said, ask them of the manufacturers, and try and get answers from the manufacturers, because they're really going to know the most information, or maybe not, about all of these questions.
Yep. Great.
Great. Yeah. So that's dose, and that's really the most important takeaway here is go to a company and say, prove to me that you can deliver so much of a dose, and prove to me that that's enough of a dose to kill germs. So moving on, how can you achieve high dose of air disinfection? As we've discussed now at length, in a duct flow scenario, you're going to have high velocity, you're going to have large volumes of air. Certainly the UV will help. I mean, it'll do something, because every time a UV photon hits a virus, it's going to zap that virus with some probability. And so, some UV will always be better than nothing. The question is that enough to justify the cost and the maintenance and so on? Another technology, and interestingly, this is the technology that they used in the 30s for air disinfection. It was not duct flow; it was so-called upper room air disinfection. So the way you do this is you have some sort of a setup which carefully controls the emission direction. So this picture here, I hope everyone can see it on their screen. You can see this bluish glow at the top of the room. Only illuminates the top about 12 inches of the room with UV light, and given enough airflow within the room over very long durations, this will deliver a significant dose to the air. On the one hand, it's harder to control the airflow. It's not like a duct where you know exactly what the airflow is. On the other hand, because it's just on all the time, and because the air is moving rather slowly, it's more feasible that you could actually get a significant dose over time. So you're gaining some dose, you're giving up some control. But from what I've seen from the UV disinfection experts is that this is actually what they're recommending over the AC level disinfection of air.
Yeah.
Because you're able to deliver higher doses. And this product exists. So this has been around. This exists in buildings with, for instance, occupants with sensitive health needs, places where you really want to just layer on every level of disinfection that you can possibly get. This will be a good additional layer of disinfection on top of all the other things that you might be doing, like chemical disinfection of surfaces and physical distancing and so on.
Yeah, we see these in medical office buildings. In fact, I saw these recently during an audit of a medical office building, and they'd done a very nice job in painting the wall purple, so it just looked like a standard upgrade.
Oh yeah,
nobody
that's
would
clever.
know what it was. So there are even aesthetic ways that you can make this blend in. Although maybe today you want to really show it off.
Yeah, that's right. Yeah, maybe you do want to show it off. So a few things to note about this that I didn't add to the slide, but just a few comments I want to make. So first of all, this bluish glow that you see in the photo there. Sometimes people ask, oh, is that UVC? Is that what UVC looks like? The answer is no. UVC is invisible. You cannot see it. However, all currently existing UV sources, maybe not all, but certainly most UV sources that you'd see in a real world application, in addition to generating UV light, also generate a small amount of blue light, or perhaps even violet or near ultraviolet light, which is visible to the eye. So what you're seeing there is just a byproduct of the UV light source. It's not actually the UV.
Yeah.
Sometimes people ask, is there a way to just look at a UVC light source and know for sure that it's actually UVC? And unfortunately, the answer is no. There's no easy way. You cannot rely on this bluish glow. You might imagine if there were some fraudulent company out there trying to make a fake UV disinfection system, they could just put blue LEDs in there and they would produce the same bluish glow, but of course there'd be no ultraviolet in there. So that's one thing to look out for. The other thing that I wanted to point out, which I which I didn't include on this slide because it's not quite as relevant in building scale applications, are portable air filters. So they have now portable HEPA filters that also include a UV component. You can find these primarily in the residential market. They're probably a bit too expensive to implement on a large scale. If you imagine you had a school and you had to buy one for every classroom and each one costs $1,000, that's probably not the most cost-effective way to improve your air quality. So that's why I didn't include it, but that does exist as well. So just some takeaways. What we do know is that high doses are needed, and it's unclear how much of a dose any particular system is going to be able to deliver. But that being said, you can feel confident that you will get germ reduction for sure. So a UV system will never hurt. It will always help at least a little bit. And the question you need to ask is always, will I get enough of an effect out of this system for it to be worth the cost? Another thing I just wanted to go back to is that we're talking about COVID, but there are a lot of other claimed benefits of implementing UV in your air disinfection system, such as reduced odor and improved health generally, as well as they claim improved system efficiency and reduced coil maintenance, which might be important to you as well. And again, the number one it's number 3 on here, but the most important takeaway always is that fresh outdoor air will have lower COVID levels than even the most carefully treated indoor air. So outside air, whenever possible, is going to be the way to go.
Chris, we are getting a bunch of questions about the negatives here, and I just want to cover a few of these while we're here.
Sure.
Question is, what's the potential for unintended harm here from UVC light? Eyes, skin, maintenance issues, those types of things.
Yes, definitely. So I do have a slide towards the end on pros and cons, but I don't want to give the impression that I'm trying to only tell you all the positives. I do want to give you an idea of the potential, and so that's what all of these things that I'm listing, I guess I should have mentioned in the beginning. These are really all potential positives of a UV system, and not every UV system will have all of these benefits. I just want to give you examples of the type of things that you can do with UV, but yes, of course. So the reason UV works so well, as I mentioned, UVC works so well, is that it attacks DNA directly. So anything with DNA in it will be harmed by UVC light. So that includes skin cells, that includes your eyes, and that's an important takeaway. And I will mention that again towards the end, but these UV systems need to be operated and maintained by trained professionals, or built in such a way that the UV light is completely enclosed and will not be leaking out and allowing residents to be exposed. The good news is, because it's not a chemical, it's not some sort of vapor that's gonna get everywhere. It's not gonna leave a residue. It's just light, right? So just putting something in front of it to cover the light will completely protect you from the UV radiation. So that's one of the good things about it. And I'm always careful using the word radiation. Maybe this audience already knows this well, but radiation just means light. The word radiation just means light. So blue light is radiation, red light is radiation. So I just don't want to give any sort of indication that this is anything beyond light. It's just light with a specific wavelength that's very useful, but also potentially dangerous. So that's a good thing to add. So like I said, I will get to a slide listing most of the main pros and cons, but I want to come back to this story about the meatpacking plant and come back to this question of, could UVC disinfection have prevented this outbreak? Unfortunately, the answer is kind of complicated. What we can say is that UVC alone, probably not. Just if they had done everything exactly the same, but just had some UVC bulbs in there, probably wouldn't have made a huge difference. So this is not a silver bullet. This is not going to solve all of your problems. But what I would say is that as part of a multi-layered disinfection system, there's a pretty good chance that UVC could have improved the outcome. And that might include air disinfection, but also disinfection of surfaces. And again, very importantly, this is on top of HEPA or other high efficiency filtration methods, chemical disinfection, and physical just cleaning of surfaces and all the other measures that we all know about. So the takeaway here is that UVC is going to be a complement to all these other systems. It's going to be something you layer on top of everything else. It's not going to be a replacement for any of these systems, and it's not going to be a magic silver bullet to take care of everything. I just wanted to add, so this is an article that came out 2 days ago, and it had a quote from an ASHRAE member. And I just wanted to point this out because, again, I'm not an expert on air conditioning at all. My expertise is really only on the science of UVC specifically. But I just wanted to point out that they're saying they're not recommending any major modifications. They're not out here saying that everybody needs to get a UV system for their air conditioner. They do recommend high efficiency, so they're recommending MERV 13. Many audience members probably know a lot more about what that means than I do, but they are saying that simply going to a high efficiency filter is going to do a lot to prevent airborne spread. And it also has the added benefit of being plug and play. Your AC system is already set up for physical filtration, so it may just be as simple as swapping out one filter for another. So I just wanted to point out that this person from ASHRAE is recommending
that's
this.
consistent with the ASHRAE task force member that we had on a webinar, which again is
recorded.
I see. And for those of you that were on the MERV webinar as well, now you know more about MERV 13, 14 than you ever cared to know. So those are great resources.
There you go.
Established recommendations.
Yep, great. So just moving on. So I only have a few more slides here, so just want to get through these quickly. Just really quickly, I've mentioned this several times, but air disinfection, and this is not my word, but the experts on this have referred to it as a Wild West. It's pretty new. It's regulated the same way that pesticides are regulated, which kind of shows you how non-specific the regulations are. But the EPA does require that the product has to do what it says on the label. So at the very least, whatever the company's claiming it can do, it has to be able to do that. Many reliable companies, I don't want to say all, but certainly many companies have data to back up what they're claiming their product can do. It might be readily available on their website, or you might need to ask for it, but do ask for it, see what they have. Not even necessarily because it'll tell you all that much, but just because if a company is willing to share their data with you, that's probably a good indication that this is a reliable company. There are anti-forgery cards, which many UV companies will supply you with so-called invisible ink, and it will only light up under UVC. So that can be a good way to confirm that any questionable product that you might find actually is emitting UV light. And a good thing, again, I'm sure you all know this, but a good thing to look out for is make sure that you're buying products directly from reputable companies. So for instance, I'm giving the example of ISO certification. This is all sort of common sense stuff, buyer beware stuff, but certainly be aware that this all definitely applies to UV products as well. So this is my last slide. I just want to leave you with this, a bunch of pros and cons. I'll let you sort of read this. Maybe I'm sure there'll be more questions, so I'll just kind of leave this slide up. But before I do that, I also just want to flash this references slide. I'm happy to share all these links afterwards, so you can check these out. This is where I got most of the information for this slide deck, and there's a lot more information on all these links than what I had time to share. So if this is something you're interested in digging into, there's a huge amount of resources out there for you to check out. So I encourage you to do that.
Fantastic.
But with that, I'll leave you on this slide, and I'll thank you for your attention.
We'll distribute the deck with the links as well. We got a ton of questions, so let me see if I can take them. If you've got more, let's get them in the chat box so we can QB them. Okay, so let me scroll back up here. Okay, this is a con question, but it's right on this slide. What about plastic and fiberglass? Is there a danger of degrading from this wavelength of light?
Yeah, right. So I have this sort of cryptic may degrade plastic materials. Like, what does that mean? It's complicated for two reasons. So there's two points I want to make. Much of the research on this will be talking, they'll take some specific polymer with a really long unpronounceable name, and they'll say this polymer degrades at such and such a rate when exposed to UV radiation. And it's not, it's useful to a scientist. It's not so useful in the real world. And so unfortunately in the real world, you may just need to rely on trial and error. This is something that the manufacturers will probably be able to tell you, but as a general rule, you will need to consider using materials that are compatible with UVC light. And just like if you leave something that's made out of plastic out in the sun, it'll degrade over time. So it's the same sort of idea with UVC, except of course because the energy is higher, it might degrade faster. But if you're thinking about installing a UVC system, and especially if you're thinking about custom building one, you're definitely going to want to keep this in mind. And as a rule of thumb, maybe avoid plastic or rubber and try and stick to things like metal, because metal will not degrade in UV.
Yeah, similar question here. I don't know if this has ever been studied, but someone saying that their coils are of course lined with, have an antimicrobial on the coils. So if you're using UV to sort of keep the growth off the coils, is that gonna be a double whammy for you?
So I would guess yes. I mean that is what these coil systems are advertised as doing.
Yeah.
The UV lamp directly illuminates the coils. I don't know anything about what these antimicrobial coatings are made out of, so I don't know if the UV would maybe not be compatible with those coatings.
Yeah.
But as far as what it's doing, yes, the idea is the same, is that it would prevent any sort of buildup of biological material on those coils.
Yeah. By the way, someone comments, by the way, also look at wire insulation, which of course degrades very quickly in all kinds of lights.
Right, for sure.
Okay, tons of questions about doses. How do we figure out what power we need for CFM? Here's my static pressure in the air handler. Tons of just dose questions. Of course, that's going to be manufacturer specific, but I guess I just want you to, I want to ask personally to you, is there bench science on the dosage needed to kill this virus in any meaningful way?
So I mean, if there is, I haven't seen it, and there's certainly not much. So again, going back to this question of dose, there's two parts to it. There's how do you even calculate what the dose is in your system? That's not easy in air the way it is in water and surfaces. And then what dose do we actually need? So that's really, and certainly anything like, I have such and such a flow rate, what's my dose going to be? That I definitely will not be able to answer.
Yeah.
But from what I've seen, my confidence that you'll be able to achieve the types of dosages that you need in a high velocity air duct, I haven't really seen much science to back that up. So I would not be as confident about that as I would be about, the equivalent case, but in a water flow situation.
Right. Exactly. Okay, we're at the hour here. I'm going to wrap this, but I'm going to wrap it with one question, which is all of us have to make personal risk decisions every day in this new world. When you go into a building, are you looking for masks and social distancing signs, or are you calling up the building engineer and asking him what's in the return air duct? Where do you position this in your personal risk?
So for me personally, I'm always going to be most interested in mask wearing and physical distancing. Chemical cleaning of surfaces is also going to be a big one, as far as buildings that I'm going to be inside of. Mm-hmm. So disinfecting the high touch areas, and there are surface disinfection UV systems but they're, they require trained operators, and probably aren't the simplest answer for disinfecting high touch surfaces. So I would say that UV air disinfection for me personally is probably pretty low on the list. And on the other hand, if this were a building with occupants with sensitive health situations where they really just need the cleanest possible air they can get, there it might make more sense.
Yeah.
And again, as an additional layer on top of all these other things, it's helpful, and I'm sure it can't hurt. But for me personally, I would put it behind many of those other measures that we're all familiar with on the list of priorities.
Fantastic. Wonderful. I'll wrap it there. Chris, fascinating and so refreshing. I mean, I feel like we really got to learn something about the fundamental science and where we are on this. So I hope it's useful to the Gridium community, and we'll of course distribute the materials, and we look forward to seeing your LEDs hit the market in I don't know how many years it'll be, but UV LEDs are the future. So we look forward to seeing the impact of your research, and best of luck with the PhD.
Great. Yeah. Thank you so much. And thanks again for having me. I hope everybody learned a little bit, and I really enjoyed it.
Great. Thanks, Chris. Thanks, everyone.
All right.